Let me finally just take you near Salt Lake City to the Wasatch Front here, where we're interested in groundwater flow in the Wasatch Mountain block here. We're interested in it, but unfortunately we don't have any monitoring wells up there. We've got lots of them out here, however, so we're forced to sort of take a tomographic approach. We're going to make measurements out here and try to say something about what's going on up here. For a long time, there's been a concept that most of the recharge to this system is a result of infiltration in the mountain block, followed by deep subsurface flow and then lateral inflow into the basin. When I first encountered this concept, the geologist in me said, this is nonsense. I thought that for two reasons. A, Salt Lake City is bounded here, the Salt Lake Valley is bounded by a big normal fault, the Wasatch Fault, and it's known to be highly mineralized. And I simply didn't think that this fault had the permeability to pass significant amounts of fluid across it. Secondly, the mountains themselves are cored by crystalline and metasedimentary rocks that in order to have any appreciable porosity and permeability, they have to be fractured, and they're just not known to be fractured to any significant depth. So my geologic intuition said this concept doesn't work. Well, fortunately, one has graduate students that don't necessarily believe what their advisor thinks. Here's one of them, Andy Manning. Andy reasoned that I could evaluate this flow path by using noble gas thermometry. He reasoned that this flow path should have a cold noble gas recharge temperature. In contrast, fluids that came down in these ephemeral streams and then infiltrated through a thick unsaturated zone and finally had their noble gas thermometer set at the water table at depth, they would have a warmer recharge temperature. So that was the idea. Andy went out into this system, collected lots of samples. There's so many that I can't even put the data points here on the map. And here's some of his results. This is a contour map of the probable maximum recharge temperature in this system. It's the probable maximum temperature because anytime you make a measurement of one thing and you use it to then infer something else, you should propagate the uncertainty that's associated with those measurements and the whole analysis, the inversion and so forth. We've tried to do that, and these are the probable maximum temperatures of recharge. If we look at what recharge temperatures could possibly exist in the mountain block, well, they should be less than about 10 degrees C. If we look at what recharge temperatures should exist out in the valley fill, they should really be greater than 12 degrees Celsius. And not good news for me, you'll see that there's large portions of this system that have colors that lie in this mountain block region. Andy has further quantified this in terms of the probable fraction of that fluid that was derived from the mountain block. And you can see a big chunk of this that has 70, 80, 90% of the fluid that appears to be derived from the mountain block. So I think I was wrong about this. The noble gases tell us where this fluid might be coming from, but it doesn't really tell us quantitatively anything else. So for that, we wanted to make use of these dating techniques. Here was the idea. We reasoned that if fluids were taking a deep looping flow path through the mountain block, they would be relatively old out here where we could sample them. In contrast, shallow, rapidly moving fluid should have a young age here in the basin fill. This was a good idea, but it didn't work very well. It didn't work because the absolute age of this fluid also depends on the effective porosity of this fractured mountain block. And we're no different than anyone else. We don't have an independent constraint on that. So we had to take a different approach. And that's sort of illustrated as follows. Imagine a case where there was very little flow in the mountain block. That might produce an age distribution out in the valley that might look like this. Contrast that to this next picture, a case where there was a lot more recharge. The spacing on these contours would be vastly different. So we reasoned that instead of using the absolute age, we should use the gradient in the age distribution to say something about the horizontal fluxes and therefore what the vertical fluxes were back here. We also reasoned that we had another tracer that was almost free to us, the physical temperature of the water. Here's a simulation, Forster and Smith, in which the fluid flux is so small that you effectively don't alter the geothermal field. In contrast, a large fluid flux that effectively robs heat from the mountain block. And although conceptually we can't sample up here in the mountain block, if we look at the difference in the temperatures out here in this receiving well that's conceptually out in the valley, there are big differences here between these two models. So heat might be a good tracer. Let me just really quickly show you some data. Here are some tritium-helium ages that we've measured. Young waters, 5, 10 years or so on the fringe of the basin, they systematically, in a rather smooth and contourable sense, get older and older as we move out and towards the central portion of the basin, to about the limit of the tritium-helium dating technique. The temperature of the water, the physical temperature, looks a lot the same. We have cold water on the fringe of the basin, and it gets warmer and warmer as we move out and towards the middle. So how do you take all these sorts of data and put them together into a single statement about the groundwater flow system? Well, of course, you put together some kind of a model. And here's the region of the system that we attempted to model. This is a saturated, unsaturated model. We had to do that because we don't know where the water table is up here in the mountain block. All we can do is postulate fluid fluxes, and then we have to let the model put the water table where it wants to be. We tried to set this model up so that we could turn on and off layers at depths so we could examine shallow flow paths and deep flow paths. And what we've really done is tried to cast the results of this in terms of the two primary uncertainties that we have about this system. How deep do fluids circulate, and then how much recharge is there. So what we've done is a whole bunch of simulations, and each one of these is very CPU intensive. They take days to weeks to do. And what we're really asking the model to do is not tell us what the answer is, but rather what the answer probably is not. We're trying to rule out portions of this solution space that don't fit our observations. So for example, if we look at something like stream flow up in the mountain block, we find that these simulations simply don't produce anywhere near the amount of stream flow that we observe. So we say that they're improbable. We rule out that portion of the solution space. If we look at the absolute age of the water, we rule out a little bit of this solution space, but not very much because of this big uncertainty in the effective porosity. So it doesn't help us too much. If we look at the temperature of the water, we find we rule out a big chunk of this solution space. Simply put, if we had recharge rates in this region, they should produce colder water than on average we observe out in the valley fill. So we deem this to be improbable. And finally, if we look at the age gradient, we rule out another portion of this solution space. So how deep do fluids circulate in the Wasatch Mountain block? We don't know. We have not been able to objectively rule out any of these depths. All of these depths are possible. However, I think we have been able to constrain the recharge rate. And if you compare our range of possibilities to previous estimates, you find that we're on the low side. And I don't think that's a new theme. It's kind of interesting in this system, if you look at the estimate of the recharge rate as a function of the date of the report, here's what happens. Things just go down. This is a bad thing to show to water managers who fund some of your work, because they say, if we don't stop doing these studies, we'll have no water at all by about 2020, so no more recharge studies. If you do your best at quantifying the uncertainty in these measurements, what you find is that there was nothing wrong with these earlier studies. They simply were constrained by less data. They have larger uncertainties. And while our most current estimate has the smallest error bars, it is nevertheless on the low end of this. And I believe that in this system, like many systems, we have systematically overestimated recharge to these big mountain basins. And I think if you combine that with a notion that we are likely overdrafting many of these regional aquifer systems. Here's one isolated example in central Turkey, the Anatolia Plain. Beautiful window into this massive carbonate aquifer. This really is an underground lake, so to speak. Let's zoom in here. Here's a pumping station. There's the intakes of this that was built in 1970. So tens of meters of drawdown in this absolutely massive aquifer. And why? All due to agricultural pumping. Recent editorial in Groundwater by my good friend and colleague Ronit Nativ, questioning whether or not Israel can continue to use the amount of water it does from the coastal and mountain plain aquifer for agricultural purposes, or as she puts it, growing tomatoes to ship them to Europe. Bill Alley, Chief of Groundwater Science for the USGS, quoting Postel, groundwater depletion may be the single largest threat to irrigated agriculture, exceeding even the buildup of salts in soils. And indeed, the International Atomic Energy Agency would estimate that something like 50% of all water, all groundwater that is used for agricultural purposes is fossil water, 10,000 years old or so. And I find that very sobering with respect to developing these groundwater systems in a sustainable sense, indeed, in a sense of feeding the world. So, can these noble gases help us with any of this? And what have we learned? Well, at these till sites, I would claim that they're being helium leak tested. And I think they're passing that test. And we should therefore utilize these systems for isolating waste. We simply cannot afford to put waste in aquifers or in contact with them. At Cape Cod and these other humid sites, I think we're learning that a direct or nearly direct measure of the spatial patterns of recharge is exceedingly important to understand the detailed nature of plumes. It's as important as understanding the detailed distribution of permeability. The noble gases are one thing to help with this, but there's a lot of other techniques in soil physics that maybe we're not making as much use of as we should. In southern Utah, we're actually trying to put water back into the ground, but we're not doing such a good job at this because I think we've plugged this system up with air. I'll go so far as to say that I think that the next generation of hydrogeologists will be as involved at trying to put water back into the ground as my generation has been at trying to take it out. That's going to happen if we're going to reverse these trends of overdrafting these big aquifer systems, but we're going to have to learn how to do them without plugging them up. And plugging them up with air is just one of a very long laundry list of plugging issues, biofilms, swelling of clays, etc., associated with aquifer storage and recovery. And then finally, at the Wasatch Mountainside, I guess I've learned the obvious. A, it's really good to have graduate students. And perhaps the other obvious is that the more data that you get, the more that you constrain these problems. And that turns out to be important in this case. As a final statement, let me come full circle to Henry Darcy. He was more than just an outstanding scientist and engineer. He certainly was that. But in my read of Henry Darcy's life, he was an extraordinary citizen. Many of you may know that he refused the fee that he was offered for designing the famous fountains of Dijon, valued in today's dollars of $1.5 million. And while I'm not suggesting that we work for free, I think that if we will take not only Henry Darcy's science and engineering, but if we will take his concept of citizenship, I believe that he felt like that since he was privileged and he had this college education, he ought to take that and return it back to society. And he spent his whole life doing that, not just working on, infiltration, Darcy's law, but a whole range of hydraulic issues. I think if we'll take Henry Darcy's citizenship, along with his science and engineering, that these kinds of problems and others are solvable. Thank you very much for your attention.